Okay, now we're going to determine whether a function is even, odd, or neither. The three options are a function can be even, a function can be odd, or a function can be neither. Now, I want to tell you right off the bat, we do not determine if a function is even or odd by its degree. The degree of a function, if a function has degree, most of the ones we've studied so far have degree, but a degree of a function does not determine if it is even or odd. It's more fun than that. So how do we determine if a function is even or odd? Or let's look at even first. We'll look at odd after this. To determine if a function is even, we want to see, we define an even function as being symmetric about the y-axis. That means that if we were to reflect this function across the y-axis, it would give us the exact same function. If we want to see, one way we can determine is to graph it. If we want to see if the function f of x equals absolute value of x plus 1 is an even function, we can graph this and do math, num, absolute value, and type in x plus 1 and graph this. And that function is obviously not a reflection of itself across the across the y-axis. Therefore, it is not even. It's not even because it's not a reflection of itself across the y-axis. On the other hand, if we graph f of x equals the absolute value of x, then plus 1, so the plus 1's on the outside of the absolute value, and graph that, now if you notice, this is a reflection. I want to zoom in here to show you. This graph is a reflection of itself across the x-axis, or the y-axis. Therefore, this one, by the graph, you can see this is even because it is a reflection of itself across the y-axis. Another way, because sometimes a function could look symmetric about the y-axis, look like a reflection of itself across the y-axis, but really not be, if it was really, really close to that. But another way that you can analyze it is by plugging in an arbitrary value of x. And when I say arbitrary, I don't mean pick a number. You can pick some random numbers and plug in f of 1 and f of negative 1, because those should be the same if this function is symmetric. In fact, if f of x equals f of negative x, then f of x is even. So you could look at that by picking some random values of x. Say you want to plug in 5 for x and negative 5. And if those two values were the same, that would suggest this might be even. You could try another one, plug in 1 and negative 1. If those two values are the same, it might be even. But it doesn't guarantee that, that they're the same for all x and negative x. So the way we check this is we plug in an arbitrary value, one that we don't know. We plug in a, and we get a squared minus 2a plus 3. And then we compare that to f of negative a. So if I plug in negative a for this function, I would get negative a squared. Plug in negative a for x and get negative 2 times negative a, and then plus 3. And when I simplify that, negative a times negative a is still a squared. That hasn't changed. But negative 2 times negative a is now positive 2a plus 3. These two values, a squared minus 2a plus 3 and a squared plus 2a plus 3, are not equal for every value of a. Therefore, since f of a does not equal f of negative a, f of x is not even. If we look at this other function, f of x, on the other hand, and try f of a, now notice the negative is not in parentheses here. That means only the x is squared. It's like negative 1 times x squared. So when we plug in the a, the negative stays out front, and we just plug in the a for x. And that gives us f of a equals negative a squared plus 3. And now if we plug in negative a, now we have negative a squared plus 3. And since negative a squared is a squared, we still have negative a squared. And we get negative a squared plus 3. And f of a is equal to f of negative a. Therefore, we know that this is an even function. So f of x equals negative x squared plus 3 is an even function. If you were looking at this on a graph, like we did before, you could look at it and see if it's a reflection across the y-axis. If you're looking at a table, if f of 2 equaled 3, if the function was going to be even, f of negative 2 would also have to equal 3. Every x value and negative x value, so for any value you plugged in for x and its opposite, they would have to have the same y value. If you look at a table, that's the table. If you look at a graph, then the symmetry across the y-axis is pretty obvious. So an even function according to our algebra definition is one that is symmetric about the y-axis. And analytically, algebraically, it means, and if a function is even, then f of x equals f of negative x for all values of x in its domain. And that's how we tell if a function is even.